It's my great pleasure to introduce today Dr. Steve Dawson from the University of Otago in New Zealand. Department of Marine Science there. Steve has been visiting with us. He's on sabbatical or study leave, as they call it. He's been with us for 6 weeks, which has absolutely shot by. It's been remarkable effort the time has gone, which means we've been having fun and being productive. So it's been great to have him here. Unfortunately, he goes back to New Zealand tomorrow. Steve is a very well-known, internationally known and respected marine conservation biologist. He and his partner Liz Slutin, who's here in absentia today, are known for their work on the genus Cephalorhynchus, or some people pronounce it Cephalorhynchus, of which this is one member. And they are two of the most prominent marine conservation biologists in New Zealand. We were saying this morning that our careers have had eerily similar parallels. We both started out working on bycatch of small cetaceans, Steve and Liz with Hector's dolphin in New Zealand, and me with harbor porpoises in Canada. And we've kind of learned how not to do things through experience over time. I think Steve will share maybe some of that with you today. Steve is also, I should say, the recipient, Steve and Liz, were recipients of the Sir Charles Fleming Award, presented by the Royal Society of New Zealand for outstanding contributions to conservation science in New Zealand. So we're very fortunate to have him here. I'm glad so many of you have shown up, and I won't waste any more of Steve's time. So, Dr. Dawson.
Thanks, Andy. There's so many embarrassing things you could have said that didn't. So that's very nice. And I want to say right at the outset two things. The first is that what I'm going to talk about today, I'm going to try and talk about 25 years of research in 45 minutes. So it's going to be something like time travel. And the second thing is we're going to have to gloss over some details in order to do that clearly. And the second thing is most of this work is done by myself and Liz Slutin, so I don't want to appear as if I've done all this. There's also a squadron of graduate students behind this, and they all should share the credit or the blame, depending on your point of view. So, if this is going to work, that's the one. So let's talk about how I'm going to structure this. First of all, I want to give you a little bit of an introduction to the species. Next, I want to go over, in kind of chronological order, the way in which we tackled this problem. It kind of started with these four elements. It's had these four elements. First of all, discovering the problem, research to get the first protected area in place, some strategic research to support further protection because we recognised that one protected area wouldn't be enough. And the long-lasting theme of our work has been about testing the effectiveness of management. And at the end of that, I want to offer some lessons that we've learned in New Zealand for science and management generally. So let's start with the species. They're absolutely remarkable animals. The first thing that strikes you is their size. They're tiny. A really big one is 1.4 meters long. I translated this into American for you. When are you guys going to go metric? Come on, get with the program. They're found in very small populations. The South Island population is considered endangered, and the North Island population, which I'll talk about obviously, is considered critically endangered. And the genus is extremely interesting. There are 4 species in the genus. They're all coastal inshore animals restricted to a small part of the southern hemisphere. We have Commerson's dolphin, which is found off the coasts of Argentina and the Falkland Islands, and there's an isolate of it, very interestingly, at Kerguelen. Those animals at Kerguelen, all of these animals have got they start off life with the full adult colour pattern, but there's overlaid on that, there's a kind of a darker hue, which they grow out of. These animals retain that into adulthood, and they've also got a different number of sternal ribs, the ribs that articulate onto the sternum. So it seems that that's a founder event that's driven that, and the genetics bear that out. We've got another species which is off the coast of Chile, not surprisingly called Chilean dolphin. We've got another one which is off the coast of Heaviside, and that's this one here, Namibia, South Africa, named after the guy who discovered it. And we've got Hector's dolphin in New Zealand. And this is what they really look like, and you can see immediately that Hector's dolphins is by far the best looking. In fact, I joke with Andy that Hector's dolphins are everything that harbour porpoises should be but aren't.
What about New Zealanders?
So we started a long, long time ago. I see we're losing a little bit off the edge here, but that's no big problem. We started a long time ago when we were both a lot younger, and I had hair. And we started off with this tiny, tiny boat, and we'd just finished our master's degrees, and we were wondering what we were going to do next. We didn't have a PhD organised, and so we thought, but we did want to work on Hector's dolphins, so we thought, no one really knows where they are, and no one's got the foggiest idea of how many there are. So we would do this extraordinarily sort of crazy survey, really, of most of the South Island coast in this 4-metre boat. If one of my graduate students mooted this idea today, I would say, you must be joking. However, we did it, and I calculated this out. This is just a fun statistic. We covered 4,500 nautical miles, which is 2 million boat lengths. And so, measured in terms of boat lengths, we won the longest survey we've ever done. But it produced the first decent data on distribution. And our estimate of abundance from that survey, it was a strip transit survey, was about 3,400. Now, during that time, what we would do is we would launch from all these tiny little places around the South Island, and we'd go sort of 30 or 40 nautical miles up the coast and come back again and make counts either way and use the standard kind of strip transit methodology. And we would try and talk to the fishermen wherever we went, because clearly they were a repository of a good deal of knowledge and experience, not just about where the dolphins are, but local weather conditions and so on. So we made it our business to talk to as many of them as we could. And it became clear in those conversations that many of them said, I do catch the odd one. And it became clear in those conversations that bycatch of Hector's dolphin was a real problem, and not an infrequent one. And that's the situation that's shown in this picture. We, however, we were fairly pointy-headed at the time, I have to say, and we'd intended for our PhDs to focus on, Liz wanted to focus on behaviour and how different kinds of behaviour events related to other behavioural events to try and understand what behaviours mean and so on. And I was a kind of an acoustician at that time. I was interested in, Doug will tell you what kind of an acoustician. I was interested in their sonar system, how that worked, how they used their sounds, whether that had relationships with their social behaviour and so on. So we started off with this kind of very pointy-headed kind of academic outlook, which I'm not denigrating, by the way, but it's just that things did take a different turn, because we put out the message amongst the fishermen that no one really knew what the sound source was at that time inside dolphin heads. So I was really quite keen to do some dissections of that to try and see what we could figure out. And Liz was also keen to do some dissections to see if there was if there was seasonal cycling, for example, in testis sizes there is in many marine mammals, and see if that had any influence on behaviour in some way. So we put out the message that we wanted to get carcasses, and we were just swamped. We were simply swamped. And it became clear to us then that there was a very serious problem that we simply had to address. We couldn't walk away from this. So one of the things that I started doing is I started a formal interview program. Obviously, interviews of fishermen are not the best way to gather bycatch data, but we couldn't afford to do anything else. And if you just simply added up the numbers that the local fishermen told me, 230 dolphins got killed in gill nets between those 4 years, between 1984 and 1988. And incidentally, we've had the same kind of catch rate confirmed in a camera trial of having cameras on boats, remote cameras on boats, and in an observer program. So those data seem to be more reliable than you might think. They are caught in gillnet fisheries. They're caught in gillnet fisheries mostly for these two species of fish, elephant fish, which is a chimera, and rig, which is also known as spotted dogfish. And this is where the fish and chips comes in, because both these fish are fish and chip fish. Their major market is for fish and chips, which is considered a New Zealand delicacy. I suppose that tells you something about New Zealand cuisine. They're standard gill nets. They're used from boats that are pretty similar worldwide. The nets are reeled up on, they're set like this on the bottom. They're reeled up on that giant cotton reel looking thing on the back. And they're really set continuously. Unlike several other gillnet fisheries, they're really set continuously. So they'll go out and they'll set the nets, and they will remain set until they come back the next day and work the nets again, and then they'll immediately reset them. So the only time that they bring the nets back to port are when they anticipate a storm that's large enough to perhaps lose some gear. We also, like you here in North Carolina, we have that thoroughly cancerous phenomenon of amateur gill netting. We have it. These are two shots of amateur gill netters at their work. This guy is fishing inside a marine reserve and inside a marine mammal sanctuary illegally. So we have big problems with these guys obeying the rules. It turns out that they're a much more significant contributor to the catch of dolphins than you would think to start with. But the advantage of having this catch, I mean, when that kind of thing happens, it's nice to be able to get something positive out of it, and that means that there are carcasses available to do things like aging, tooth aging, and you can see from this that this animal is, we have a light and a dark stained layer. This is laid down before the animal's born. We have a light and a dark layer for representing a summer and winter's growth. And so each light and dark layer represents one growth layer group. This animal is 7 years old. And we can also look at their reproductive organs, which tell us a great deal about what's been happening. This thing on the top there, this corpus luteum, is what happens when the animal ovulates. It happens when more than half of you ovulate. This is what I shouldn't probably know more about mammalian physiology than I do, but what this does is it secretes hormones madly that sustain the pregnancy. So it's what drives the whole pregnancy process, maintains the uterine wall into a condition that's suitable for implantation and so on. If no pregnancy occurs, or after the pregnancy has happened, they shrink back into these whitish, warty-looking things called corpora albicantia. So the upside of that is that you can look at an animal's ovaries and tell immediately, without sectioning or anything, whether that animal is reproductively mature. Interestingly, these ovarian scars seem to be permanent in cetaceans. They're not permanent in humans. So that's an interesting point of difference. You can also quite easily tell if an animal's been pregnant. They give birth to their young are quite large when they're born. They're on the order of about 80 centimetres long, and they weigh 8 or so kilograms. There's no pelvis to get in the way, which is an awfully good thing if you're going to give birth to something that's that size. But you can imagine that your insides are pretty comprehensively stretched out when you've got something that's 8 kilograms inside you. And you can see these kinds of stretch marks, these serosal stretch marks in the uterus that tell us absolutely that this animal's been pregnant. So you can, by looking at in the dissection, you can tell if the animal's reproductively mature, and you can tell if she's been pregnant. You cannot tell how many times she's been pregnant, and you cannot tell how many times she's ovulated. And the reason for that is that sometimes, as humans do, sometimes they'll ovulate more than one follicle at once. It would be lovely if you were able to look at their ovaries and reconstruct a reproductive history of what this animal's been doing, but you can't do that. So for that, the best estimates of calf interval, we've got to go back into the field, which is really the fun, but especially after doing lots of dissections. These are, what we do here is we've got a photo ID catalogue of as many individuals as we can who've got distinctive scars like this one, white paint mark or nicks to the dorsal fin and so on. And we know the sex of many of those individuals, and some of the most valuable data that we can get is following these known females through their lifetime over a long period of time to be able to put together their reproductive history. And that's more reliable than doing it from dissections because you can't tell the ovarian scars from, there's no difference between them from pregnancy and just ovulation. So you can't look at the scars and say, well, that one's from pregnancy and that one's from ovulation. And also you can't tell whether the calf survived, and that's the crucial thing. This has a couple of consequences for us. It necessitates high photo ID effort towards the end of the season, where you want to be absolutely sure that you've got enough photo ID effort at the end of the season to detect any calves that may have been born to a particular female. And it raises the possibility of doing something that's really quite interesting, and that is putting together the lifetime reproductive history of individuals. And that's pretty useful. So if we were to sum up the reproductive biology, the females give birth first when they're between 7 and 9. They have an intercalf interval of about 2 to 4 years, and they reach a maximum age of about 20, a little bit longer than 20. If you can balance your checkbook, you can construct a population model that uses those data that will give you an estimate of the potential population growth rate. If you can balance your checkbook and you've got an understanding of basic statistics and you can write Excel macros, you can make that stochastic, and you can make it incorporate the uncertainty that you have in all of the input parameters. And the useful thing about this is chopped off the bottom, which is a bit sad, but there's a distribution here for population growth. The useful thing about that is that you can produce something that looks like this. This is something that's great for communicating with managers because it's very easy to understand. This represents the probability that the Banks Peninsula population of Hector's dolphins was declining or increasing. So you can say, if you're a betting person, you wouldn't want to bet on the green, right? Because most of this distribution is red. And that really was the situation when the Banks Peninsula Marine Mammal Sanctuary was declared in 1989. This was the set of data that Department of Conservation used to promulgate their proposed protection measures, which resulted in this area here. It's 1,170 square kilometres. It goes all the way around Banks Peninsula, which is on the east coast of the South Island of New Zealand. There are no gill nets allowed in there, no commercial gill netting. Very, very limited amateur gill netting. The other fishing methods are not changed at all. So that was protected area number 1. And I'm glossing over this, but boy, it was gained with a great deal of angst. We've got friends who refer to this kind of biology as combat biology, because there's always someone, in fact quite a lot of people, who will hate you for doing this kind of thing. Tires, slash, threats of violence, all kinds of interesting stuff. We were, at this stage, just recently employed at Otago University. We'd both got our PhDs from Canterbury University. And we took on our first PhD student, who was Stefan Brager. And one of the most interesting things that Stefan did was that he had this idea of doing photo ID at several different sites all over the South Island. And he was interested in figuring out what the movement rate was between these sites. And they were positioned, some fairly close together and some a long way apart. And what we were really trying to do is to figure out how discrete these separate populations, these apparently separate populations of Hector's dolphins were. Well, he discovered 2 things. The first one was very surprising, that even though some of these study areas are quite close to one another, for example, we would do some work out of the Westport River bar just above that little pimple there, and Greymouth is only sort of, it's less than 40 nautical miles away. We had no overlap of individuals that were photographed from Greymouth and Westport. Likewise, we've had no overlap between the ones photographed at Banks Peninsula and Timaru. And we've done the power analysis, which shows that, given the resighting rates that we know, if there had been movement of more than 2 or 3 of those animals south, we would have found it by now. So our best estimate of movement on that kind of scale is 0. He also found that by looking at the resightings of animals around Banks Peninsula, the average home range was very, very small indeed. These things, he found the average home range was 31 kilometres of a longshore coast. So you really, with Hector's dolphins, if you see animals in the same bay 2 days in a row, there's every likelihood that they are in fact the same animals. So these are real home bodies. They're as localised, I think, as probably any population of marine mammals. In the meantime, there was also a very clever PhD student working out of Auckland University, a guy called Franz Pichler, who did some very clever things. One of the first things he did was he wrote to all of the museums in New Zealand, and he asked, well, do you have any Hector material of any age? And he figured out this way of extracting the DNA from bones. And he was able to reconstruct, he was able to look at the mitochondrial DNA from these historical samples and from modern ones. And so he's been able to put together really quite a complete look. This is from quite early on in his studies, but really quite a complete look at the genetics of the species. And the interesting thing about it is that there are 4 clearly separate genetic populations that effectively don't interbreed. We've calculated out what the effective migration rate between these 2 populations has to be in order for those differences to persist. And it's something like 1 female in every 3 generations. So the effective migration rate between these populations is tiny. And that's a crucial thing because there are so many consequences of having that kind of reduced gene flow. And he also did some work on nuclear DNA, and the only point of showing this slide is to show that, and all you've got to know here is the bigger numbers mean more difference, is that you see more or less the same kind of pattern with the nuclear DNA as you do with the mitochondrial DNA, except for, in some of these populations there is much less difference in the nuclear DNA than there is in the mitochondrial DNA, which is pretty much what you'd expect. So if we move on now to the phase of, well, we thought at this time we've got one protected area. We know that the problem, however, is widespread. We need to put in place some work that we can use to see what's needed elsewhere. And the first thing we decided to do was, well, the abundance estimate needs to be revised. We did that first one from a 4-metre boat. I mean, clearly it was a long, long way from state of the art. Our mothers were sending us care packages during this thing. It really was very funny. It was also the time when I'm not a good liar. I'm a terrible liar. And we flipped our boat on the Hokitika River bar, the little one. And my mother worked from an optician at that time. And I thought, well, what I'll do, I'd lost my glasses. I wore glasses then. And what I'll do is I'll ring her up and I'll get a new pair of glasses through my mother. And I hadn't thought, God, I was so stupid. Hadn't thought, what's the question she's going to ask? How did that happen? What was I thinking? So she asked, how did that happen? And I didn't lie. I said, a wave washed them off my face. Which is probably the most stupid thing I've ever said in my life. Well, it's up there. We'd flipped the boat and we lost them, and we lost a whole pile of stuff. But anyway, we carried on. So we were very pleased to finish that survey. So it wasn't done with the best of techniques, and it wasn't done with the best of equipment. And so we decided that the best thing we could do would be to dramatically improve the quality of the abundance data. So we, Liz and I, decided to put our money where our mouth was, and we sold our house in Dunedin, and we bought this 15-metre catamaran, which we put new engines in and modified so that we could do line transit surveys from. And we lived on this boat. Well, we kind of had to because we didn't have a house anymore. We built this collapsible sighting platform, which you could literally put up in less than 10 minutes. It didn't collapse with people on it, which is good. But so our protocol was that we would sail to where we wanted to work, and we would then work there under a motor. And the beauty of displacement cats is that they're actually quite fast for very limited horsepower. This thing had 250 horsepower diesels, and we could cruise at 10 knots all day. And we used very, very little fuel, and of course, from side to side, they're really stable. So it's an excellent line transit platform. And these are such coastal animals that the ability to go into very shallow water is very helpful. So we started this really quite comprehensive program of line transit surveys, some from that boat and some from planes. Now, some of you here will recognise Andy will recognise Simon Childerhouse, who's one of our colleagues, ex-PhD student, and Will Raymond, one of my ex-PhD students. This was our pilot. He was a bit disturbing because he played in a death metal band. And we went to see them one night. And one of their songs was called Wave Goodbye to Both Your Hands. This is not reassuring. But he was very good. You'll see that it's a twin-engine plane for safety over water. I'm not sure that I buy that argument really, but people feel better about it. And we've installed these bubble windows so that you can look directly underneath the plane and count the animals that are right below you. That's very important for line transit. Luckily, they're really quite easy to see from the air. They really stand out well. So they're good candidates for aerial surveys. And we surveyed the entire east coast and north coast from the catamaran and the west coast from the plane. And there's a number of really good reasons for that. It's not just because we're too wimpy to work off the exposed west coast and the catamaran. The swell directions and so on would not have been very conducive to it because the prevailing swell is southwest. And the sun in the other hemisphere, of course, the sun rises in the east. So in the morning, when the conditions are good, you'd be looking straight into the glare, and that's just not going to work. So in an aircraft, you're much more flexible about what you can do with the swell. So that's why we did those. There are some design principles that we adhered to. Of course, you want to allocate more effort where in the high density areas, it matters a lot if you're wrong about the density in a high density area. It doesn't matter much if you're wrong about the density in a low density area. Within each stratum, we had equal coverage. We had a randomized element to this. And we wanted to achieve, how line transit systems surveys work is you want to estimate the shape of this curve. And so there are some features of the data that you really, really want. For example, you want enough data under that to be able to estimate the curve with some precision. The next thing you want to have is this very, very broad shoulder. So essentially so that the curve knows where it should cross this y-axis. And this is absolute textbook. This is as good as line transit data ever look. And we've got a paper which describes those kinds of surveys that I'm happy to forward to you if you want. But the outcome of all of that was these numbers here. It's funny how you can do so much work and summarise it in so few numbers. Anyway, you can see that what we were really worried about was the North Island, because the North Island's population estimate, the point estimate's 111. We have some other small populations, 300 or so around the northern part of the South Island, 400 or so around the southern part. And that work really has stamped the direction of the current protection measures. So all along, however, we've been working on, there have been a few, well, at this point there were 2 protected areas. The first one that we got in 1989, this one was established just after our abundance estimate of the North Island, so the abundance estimate of North Island drove this one. It was also driven by the fact that the Minister of Fisheries at that time, I don't know how it is in this country, but our politicians, some of them are quite straightforward and very easy to deal with. And it turned out where we were living on our catamaran, Pete Hodgson, who was the local minister he was the Minister of Fisheries, he lived in the same tiny village. And I would quite often meet him in the hardware store. I don't know what it is about the hardware store, but we would often meet there. And he said, look, you guys are the people who know more about this species than anyone, and I'm the Minister of Fisheries, and it seems to me that if we can't sort this out, then we both need our asses kicked. Which is a very refreshing attitude from a politician. So we worked together a bit on that, and he put in place this very large protected area. It's out to 4 nautical miles offshore. It stretches for, as you can see, about half the coast of the North Island west coast. And it includes just about all of the known Maoris dolphin distribution. So our work at this point was focused on trying to evaluate the effectiveness of those protected areas. The North Island surveys were the most depressing surveys that I've ever done, because you can fly for days and not see anything. You know, they're really extremely rare. This is an abundance estimate that was based on something like about 9 sightings. We did some relatively clever things with estimating the detection function, but because we lumped in a whole pile of sightings done by the same crew in another place with more of them. But we see the same kind of thing in wintertime. They don't distribute between summer and winter. This is a really, really intensive aerial survey. The lines are only half a nautical mile apart, and out to 10 nautical miles. So you can see, first of all, that they don't go very offshore, very far offshore. Most of the good news that this established was that all of the sightings that we made were well within the protected area. So that was good. But it did really confirm that the abundance estimate was very, very low indeed. So the question arises, when you've got an animal that's as rare as that, how on earth do you monitor its habitat use? Because we had a question about, there were some of the harbours that they used, they sometimes use some of the large west coast harbours, and we needed to know how often, because gill netting was still allowed in those harbours, and in fact there was more gill netting effort inside those harbours than there was on the open coast. So if you swam into one of those harbours as a Hector's Dolphins, you had a fairly reasonable chance of getting caught. So we turned to this acoustic approach, which is actually quite intensively used from this lab here. This is effectively an acoustic event recorder. It logs pulse sounds with any frequency band that you choose. You can set them up to listen to any frequency that you like. You put them in place for up to a month or 6 weeks or 2 months, and you go and collect them, and you can download them and figure out what you've seen, what you've detected. And the beautiful thing about Hector's Dolphin sounds is that they make sounds that are comprehensively unlike any other cetacean in New Zealand waters. So you really can do perfect acoustic species identification. So what we would do is, this is the spectrum. This is the frequency versus amplitude. So we've got nearly all of the energy is around 120 kilohertz. This is what you would see on an oscilloscope. The clicks are quite long, as dolphin clicks go. So we would set our pods up to listen at 130 kilohertz. That's as close as we could match the pods to their peak frequency. And also to listen at 50 kilohertz. And so if you had a detection at 130 and not at 50, you've categorically got a Hector's Dolphin. If you've got one at 120 and something at 50, you've categorically got something else. So it's nice to have a species which is so unique in its vocal output. And indeed, harbour porpoises are the same. These guys are very similar in their vocal behaviour to harbour porpoises. Of course, this all requires quite a bit of calibration, and we've done various things like putting 2 pods side by side to make sure that they measure the same thing. We've done quite a lot of simultaneous wideband recording with a high-frequency tape recorder and a high-frequency digital system to make sure that the clicks that you detect on this instrument are in fact dolphin clicks and are not snapping shrimps or some other radio frequency noise or whatever. And we've done some simultaneous theodolite tracking to figure out how far away do these instruments detect dolphins when they're in the habitat. And the upshot of that was in the Manukau Harbour we had 5 of these instruments deployed. What I've got here is these circles indicate where these devices were, and the range of that, the diameter of the circle, it represents the maximum detection range that we've measured from these instruments. It's not very great, and you could see that it would be really, really easy for animals to sneak past without being detected, and this is one of the things about acoustic surveys in this kind of way. They're very conservative. You can't expect to detect every time an animal comes past. You can see, though, that there's only one place where we've made 28 acoustic detections, and this is the extent of the protected area. So this area was gillnet free. This area was quite intensively gillnetted. And what the minister has done recently is a different Minister of Fisheries now, which is very sad. He has, in typical political fashion, he has shifted this boundary so that it goes to about there. The smallest possible increase in protected area that would be consistent with the data. The average detection range is much less than that. So you really can see that these data could be extremely conservative, and it's very difficult to know how you should proceed in a management context with data like these because they're so very conservative.
Steve, how much do the dolphins go in and out of that harbour? Do you know?
The acoustic data are the only data that we have to tell us anything about that because they're so uncommon that if you set up someone watching, they'll die of boredom. So we really don't know. We also did lots and lots of aerial surveys of Banks Peninsula. The idea here was to look at what proportion of the population of Banks Peninsula Hector dolphins was protected by the protected area at different times of the year. The grey zone here is the protected area. The red blobs are the summertime sightings, and the blue blobs are the wintertime sightings. We flew the same aerial survey design summer and winter for 3 years in a row. And how that turns out, just looking at the numbers, that in the summertime the sanctuary provides pretty reasonable protection in terms of distribution. About 80% of them are inside the sanctuary in summertime, but it turns around in wintertime, and wintertime turns out to be a period when they are quite vulnerable to being caught in gill nets. We've also spent a lot of time measuring survival rate, and this was done partly by my graduate student Sam Dufresne. We measure survival rate because it's an excellent indicator of population health. Of course, it drives most population models that you would put together for these kinds of animals. And our question was really, well, has it changed since 1988? And Sam's PhD, let me say that we use only the obvious marks to do this because really if you're going to look at any kind of population parameter, you need to be damn sure you're not making matching mistakes. So you want to make sure that you're using only the most obvious kinds of marks. So we use these category 1s and categories 2s, but we don't use the category 3, the subtle ones. And Sam's PhD, I kind of felt a bit sorry for him really because he did all this field work and he did this enormously detailed and careful analysis, and effectively it produced one number. And this is it, with fanfare of trumpets. So the significance of that is that it's a bit low. The survival rate needs to be, our population models tell us that the survival rate needs to be bigger than that for population growth. And he found at that stage that there was no evidence of improvement since the sanctuary. There is some new stuff on that. We've had another PhD student who came to us with a statistical background. He has a lot more data to play with because, of course, he's got 5 years more data than Sam does. And this is the distribution of pre-sanctuary survival rates and post-sanctuary survival rates. There is a significant difference here. There's a 94% probability that the post-sanctuary survival rate is genuinely higher. And I believe that, I'm not absolutely sure about this, I should talk to Andy. I believe that this could very well be the first time that anybody's detected in a population parameter a change in a cetacean population that's due to management. That's not abundance. So this is it's kind of a big deal scientifically, but any 12-year-old could tell you that this was going to be obvious. That's one of the things that's unsatisfying about science is that we spend so much of our time proving things that 12-year-olds already know. If I ask a 12-year-old, we're going to take all these gill nets out of this area and gill nets kill dolphins, what's it going to do to the dolphins that are there? If it's a bright 12-year-old, they say, well, they're going to live longer. And they do. We know that now, after 25 years of working. There's some new management that's really quite a dramatic step forwards. From 2008, the Minister of Fisheries has closed down gill netting in a very large proportion of the New Zealand coast thanks to concerns about Hector dolphins. These areas are, it's roughly to scale, these areas, coloured areas, are all closed down to gill netting. On the west coast, there's a smaller area closed down to gill netting, and it's only during the summer. We've done some work to look at the likely effects of that. This is the only equation I'm going to show, which probably will cause some minor celebration. This is a stochastic logistic model which uses these kinds of data to predict what might happen in response to those protection measures. We've got a sensitivity analysis on catch rate because that's actually not very well measured. We've got 3 options for compliance and displacement of fishing effort because, of course, in one model you assume that you take all of the fishing effort out. And in other models you might think, okay, well, what if we only take 50% of it out and the other 50% moves, and so on. This is our most optimistic version. And the reason for the colours is that they correspond with what the population is predicted to do. It's predicted to increase in these areas. It's predicted to decline in these areas. It's predicted to be much the same off the North Island West Coast. And here, these are unprotected areas, and those will just go extinct. So that's one of our other ways of looking at the likely effectiveness of these protected areas. So the good news is that our conservation problem is really well understood. The recent decisions have been a vast improvement on what was available for these animals 25 years ago. Persistence really pays off. If you're annoying enough to government, they will do what you want them to do, ultimately, if you live longer than they do. The bad news is that these animals are still declining in some key areas. Some of the populations are extremely small, so recovery is going to take a long time for them. And the fishing industry, in characteristic fashion, have taken this to court. And the court case has happened, but the judge has not yet made her decision. So all of this is a bit on tenterhooks. So I just want to now, having tried to cover what we know about this population, I want to try and see if I can draw out from this experience some generalities about science and management, because this has been a very, very much research program that has been it's driven the management. It really has strongly driven the management. And it's been responsive to the management. So what can we learn about that? Well, the first thing is that I think everybody in this room are probably going to agree, although most managers do not agree, that when you put something in place, you should study whether it works. It's interesting to see the disconnect. Many, many managers think that you can put something in place, and as long as it looks like it might work, that's good enough. The second thing is the boundaries of protected areas. This is kind of obvious. This is another thing that our 12-year-old could have told us, that our boundaries need to be biologically relevant. This seems like a stupid thing to say, but it's actually really important. Surveys can tell you where animals are. They can't tell you where they aren't. That becomes really important where you're talking about a rare species. It's very hard to prove that an area is not used by animals. You've got to have infinite effort to do that. Further work on animal ranges will nearly always increase those estimates, so there's another reason there for being precautionary in the first place on how big we make those protected areas. The more you study it, the more the bigger the home range will look to be. That uncertainty question, adding in the uncertainty that you know about these parameters is really, really important. Deterministic assessments are always optimistic. Adding in uncertainty always makes it worse. So keeping track of the variance in all of your input parameters and seeing how it tracks through the assessment is a very, very important thing to do. And long-term studies are absolutely vital, but where do you get the funding for them? I don't know how it is in the US, but there are simply no agencies in New Zealand who will commit to funding for more than 3 years. And we've run this on a shoestring from money gained from all over the place. It's been almost literally cake stalls at times. What about the management? Well, the north boundary of Banksness and Marine Mammal Sanctuary was entirely a political decision, and it was placed because there was one fisherman there who'd been really, really cooperative in the interview program. He told us about every single animal that he caught. He had just downsized from a big boat to a very small boat, and everybody kind of figured that he'd gone. If gill netting was ever going to be kind of green in the bigger picture, this guy was an exemplar of that. And we put the boundary of that protected area just south of where you fished, which turned out to be a mistake. So those kinds of political compromises can be really problematic. If we have small protected areas, they tend to shift problems rather than fix them. We found that pretty clearly. And this population is strongly fragmented to start with. And so if we have small protected areas, you could make that quite a lot worse. It's easier to make a too big reserve smaller than a too small reserve bigger. The hippies were right. Everything is connected. They really are right, especially in the sea. Big marine protected areas are inherently more ecologically sound because they include more of the kinds of linkages that are so strong in marine systems. In New Zealand, we cannot rely on public servants to be neutral or competent. Now, I don't mean to be overly insulting. I suspect it's also true in the US. But one problem is that public servants, whether they're competent or not, always have some kind of agenda that is thrust on them by the kind of job that they do. So, for example, some of the people that you got in NIMS next door are probably extremely fine. But I imagine that if you were to do some science that says that, well, we should close down all fishing off this coast, they're not going to like that because part of their mandate is to promote responsible fishing. That's exactly the situation with our Ministry of Fisheries. So you have these built-in kind of resistances from the managers that you might not, in the first case, expect. The consultation processes that we have in New Zealand, and I suspect here too, are highly biased. And they're highly biased towards the extractive users, the fishers. And this is so for several reasons, but the three main ones are that, first of all, we know who they all are because they've got fishing licenses. Their names and addresses are all down on a bit of paper somewhere, and you can contact them all. You can get them all to come to a meeting. You can have a dialogue with them. You can't do that with people who walk their dogs on the beach, for example, who might have just as legitimate a stake in the protection of a piece of coastline. Or, for example, the surfers. They've got a really, really strong investment in water quality. But are they ever included in those discussions? In New Zealand, they're certainly not. Because partly, no one knows who they are. They're quantifiable. Fish cost. Fish earn money. We can quantify what that's worth. It's difficult to quantify what catching a wave is worth. It's possible, but it's much easier to quantify extractive uses, so they tend to get valued more highly. And really importantly, because what they do earns money, they can afford expert representation at stock assessment meetings. They can afford to hire really, really, really highly skilled consultants, like Ray Hilborn, for example, has commonly been involved in New Zealand. And they can afford really, really good lawyers, and they use them routinely. And the last thing I'd like to say is that, often there's this idea that the kind of default position is that, we'll just wait for a bit longer till we've got better information. And folks don't recognise that that is a management decision. And it's really important to see that as a management decision. Thank you very much.